Heat sink. A heat sink is a passive heat exchanger that transfers the thermal energy generated by a component, like a CPU or GPU, into a fluid medium, usually air, where it can be dissipated away from the device. It is the most critical piece of hardware in preventing a thermal meltdown of your silicon components. Thermal conductivity and material choice. The effectiveness of a heatsink starts with its material. A technician will primarily encounter two types. Aluminum. This is the most common material because it is lightweight, cost-effective, and easy to manufacture into complex shapes. While its thermal conductivity is good, it is not the absolute best. Copper. Copper has significantly higher thermal conductivity than aluminum, meaning it moves heat away from the processor much faster. However, it is much heavier and more expensive. Many high-end heatsinks use a copper base, where it touches the chip, combined with aluminum fins to save weight and cost. The anatomy of surface area. The fins of a heatsink are not just for aesthetics, they are designed to maximize surface area. Since heat can only be transferred to the air at the surface of the metal, more fins mean more opportunities for heat to escape. If a heatsink is clogged with dust, that dust acts as an insulator, effectively reducing the surface area and trapping the heat inside the metal. This is the one cause of thermal throttling in older systems. Heat pipes and phase change. Modern high-performance heatsinks are rarely just solid blocks of metal. They utilize heat pipes, hollow copper tubes containing a small amount of liquid, usually water or ethanol, under a vacuum. Evaporation. The liquid near the hot base turns into vapor. Travel. The vapor travels rapidly to the cooler top of the fins. Condensation. The vapor turns back into liquid, releasing its heat into the fins. Return. Gravity or a wicking material pulls the liquid back down to the base to start again. This process is exponentially faster at moving heat than relying on the natural conduction of solid metal. Active versus passive heatsinks. A technician must choose the right type of heatsink based on the component's TDP, thermal design power. Passive heatsinks. These have no moving parts and rely entirely on the existing airflow inside the computer case. You will see these on motherboard chipsets, M.2 SSDs, and low-power processors. They are completely silent but cannot handle extreme heat. Active heatsinks. These are heatsinks with a fan physically attached to them. The fan forces air across the fins much faster than natural convection would, allowing the heatsink to handle high-performance CPUs that generate significant heat. Mounting and pressure. A heatsink is only effective if it is pressed firmly against the processor. If the mounting bracket is loose, a microscopic gap of air will form, and the processor will overheat in seconds. A technician must ensure even pressure across all four corners of the mount to prevent hot spots. As we discussed earlier, this is also why thermal paste is non-negotiable. It fills the microscopic pits in the metal surfaces to ensure 100% contact between the chip and the heatsink.